This is the call before the storm. There's an actual storm happening outside for this somehow makes it into the actual video. In a couple minutes, see if anyone shows up. If not, we'll get started here. Hello, Camille and Safa. And Lauren. Oh, good. I thought I was gonna be alone today. I would have done it. I would have trooped on, but it would have so much less fun. What's going on, people?
We're here for you, Professor. That's what's going on.
Thank you, Safa. That's fantastic because this is like one of those movies where it's like, you know, you guys like I thought you needed me, but turns out I need you. Well, it's one of those things. Welcome back, people. It's Thursday. It's basically Friday. It's 4 o'clock, but there's basically Friday. How's everyone's end of weeks going?
My lab got extended for my CS class, so I'm chilling, like chilling more than usual.
Yeah, you can put that off longer, Safa. Good job there. Yeah, let me ask you a question, because I always have my homework due Friday. Is like all of your homework due Friday? It's a massive rush to the end of the week, or is it usually chill? It's like is it the only class you have stuff to do for?
At least for me, everything is due Friday. But what you call it? This week, there's supposed to be less stuff due Friday, but a lot of stuff got pushed back to Friday, like my program 1. So that's good, but like usually like physics, let me think, I can't think right now. Physics and something. Oh, physics and intro to problem solving. That's always due Friday.
Well, now I feel bad because I think every instructor wants to give their stuff due Friday because like I don't want you to work it on the weekend. Just give it by Friday, and then you can have your weekends off. But then that means everything is due on Friday, which means if you're a student like me, that means everything is done on Thursday. But yeah, I mean, I actually say technically, I make it due. I also played with the idea of making it due. I had a class before where I made everything due Thursday night instead of Friday night because I was like, if you make it due Friday night, a lot of people are going to do it Friday afternoon. I don't want to ruin their Friday afternoon. Like I would do Thursday instead, but then I just feel like some people are like, well, what the hell? I wanted the extra day. But it's a philosophical question, really. And I dropped philosophy like 5 weeks in, so another person to ask. But anyway, and we have no more questions. We can just get started.
It's not a question, but I just want to say, yeah, I like it being due on Friday, like everything on Friday. Like that extra day is helpful.
See, Sava's put in his 2 cents. If no one else talks, that means when Sava says goes.
I agree.
Okay, Lauren Ship said, no offense, Sava, but now that Lauren's shipping in, I'm starting to believe this theory more. Okay.
That's straight. As long as it's due Friday, that's straight.
Awesome, cool. Well, thanks, Lauren, for the input. Anyway, let's share the screen and get going. So, welcome back to Discrete Math, everybody. I don't have my lights set up, so it's gonna be a little. It's kind of gloomy in here today. But I mean, that's why you do math. That's they like Cat in the Hat. It shouldn't have been them all doing all this crazy stuff with the hat. It should have been them doing discrete math. That's the way you pass a rainy day. So much fun. Specifically, discrete math. Specifically, we're gonna finish up. It's more like a review, talking about kind of what we talked about last time. Maybe looking at it a slightly different way, and then we're gonna move on to things that are new but also old. We're already at that stage. We're already at the stage of callbacks. So, anyway, let's talk about these universal conditional statements again. So looking at universal conditional statements, which remember were, there we go, which were statements that went like this. They went something like, for all x in a domain, p of x implies q of x, right? Because this is a conditional statement, and this is the universal operator. This is the universal, whatever that word is, quantifier. There we go, yeah. So that's the universal quantifier applied to a conditional statement. Now, let's recall we were kind of talking about why this is so important. Like why, like basically all of last time was me going on a rant of why this is the most amazing thing in math. And so right now, or the most important statement in math. So before we had, recall, we had regular conditional statements. Relate statements. And statements, I'll say, have a subject and a property. Basically, every single statement you make, it has a subject and it has a property. I'm wearing a purple shirt. That's saying Daniel Valvo has the property that he is wearing a purple shirt. And he loves it, by the way. That's not a statement, it's kind of subjective, but I just want to tell you guys that. Anyway, yeah, so this is my very long purple shirt. There's a subject and a property, right? So, but the problem is that then if you make, so for example, conditional statement would be that 2 is even, then 2 squared is even. Or something like, it is raining right now. I'll use RN for the kids. It is raining right now. That implies it is daytime right now. So these conditional statements, they relate statements. It's saying that whenever the hypothesis is true, the conclusion will, or it's saying if the hypothesis is true, the conclusion will follow. That's all it's saying, right? But the problem is this statement is really saying something about a subject and a property together, right? It's saying this specific subject with this specific property, it'll follow this specific subject will also have this specific property. Same thing here. Like here the subject is 2. It's saying that this specific subject 2 is even, has the property of being even, and it follows then that this specific subject squared is going to have the property of being even. And this subject, it, you can think of it as being just the time, right? Like at this time, or maybe right now the subject, at this time it is raining, right? The property is having rain and the subject is this time. And we're saying it must follow then, it does follow that this time it's daytime, right? So the point is, these are things about subjects and properties, about a specific subject, but different color. Universal conditional statements relate predicates. And predicates, they're just properties. They're disembodied properties, right? They don't even have a subject. It's just saying for X, like for any X or something like that. And well, let's do an example. So predicates are properties. They're basically just pure properties, right? And you can plug subjects into them. So for example, the equivalent here would be saying that X is even implies X squared is even, right? So here you have this disembodied subject, like the subject is X, but it's just, actually, I'm sorry. You also need a domain. So we could say like for all X in 1 to all the numbers 1 to 10. For all X in that domain, X is even implies X squared is even. So basically what this is saying though is it's saying that the property of a number being even is enough to deduce that the property, that number is also the property that it's squared is even. It's saying that this property of X squared being even follows from this property. It's relating properties, not specific statements. And that's much more valuable, right? Now we're saying the property of being even makes, from the property of being even, we can deduce that the property of being squared is even. That's much more powerful than just saying this particular number is even, and then it squares even. Much more powerful. And same thing here. So here we could say for all time, for all t in times, T, or it is raining at T implies it is daytime at T. So what this statement is saying, it's saying that we can relate the property of raining in daytime, saying that whenever it's raining, it must be daytime. We're relating the properties now, not the specific statements. We're not saying right now it's raining and then and right now it happens to be daytime. We're saying that whenever it's raining, it's also going to be daytime. Which, by the way, is this true or false?
False.
Exactly, right? I mean, it happens to be true right now, but it's not always true. Sometimes it's raining and it's nighttime. And sometimes it's raining and it's nighttime and you're driving and you hate yourself. Like, why did you decide to leave right now? The point is, yeah, and then this one's gonna be true. So that is the last thing I'm gonna say about that. I hope it's becoming clearer and clearer, like why these universal conditional statements are actually saying something kind of different. Does that make sense? Oh, we got thumbs up. Oh, thank you so much, Lauren. Yes, good. Yes, I hope it's making sense. This is the big idea. Everything we do in math is going to be related properties, so we're going to use it all the time. Awesome. So let's do a couple of examples. Actually, before we do that, I'm going to talk about implicit conditional statements. So implicit conditional statements. What these guys are just if P of X and Q of X are predicates, so just a sentence when it comes to statement you plug at the end, if they're predicates with a shared domain D, then for all X in D, P of X implies Q of X. So it's a universal conditional statement. We can write it a slightly condensed notation. Just say P of X implies Q of X, just like that. So the point is, if you see this statement right here, first of all, from context, figure out what the domain is, and then you're good. So from context, figure out what the shared domains we're talking about, and then it is that statement. So this is just a shorthand way to write this. That's all it is. But it's incredibly useful, and you've probably seen this in math, and I almost guarantee you that probably, I'm not calling the people out in this Zoom lecture, so no one has to answer, but probably I would say 95% of you that are watching this video have used this double arrow, right, in their math class at some point, and they probably didn't use it quite correctly. This happens in calculus all the time because people haven't learned what these things actually mean, and they'll say something along the lines of like, okay, x squared equals like x equals 2, x squared then equals 2 squared, which 4. Right? That's not the right way to use this arrow. Not the right way to use this arrow either. Right? These things actually mean specific things. I want to take off for it because I'm a cool dude. But the point is, yeah, these things actually have specific meanings, and this is the specific meaning. So I'll give you a quick example of how useful this could be, or like where we use it. It's going to come up later. So we don't even know all the math yet. We're gonna do some we're gonna go over the math later. An example could be prove that, or I'll say we're gonna prove this claim, and the claim's gonna be that if or for all, I'll write it in math. For all x in the real numbers, right, x squared minus 5x plus 6 equals 0 implies that x equals minus 2 or x equals minus 3, right? And you guys have totally done this before, right? I mean, you've had this factoring problem probably 1,000 times. And the way you prove it is you go, okay, proof, assume x is in R with x squared minus 5x plus 6 equals 0. Then, and so what you're doing here, right, is you're assuming that the hypothesis is true and then showing that the conclusion must be true, because that's how you prove an if-then true. So then we have that x squared minus 5x plus 6 equals 0 by assumption. And then from there, we can say this is x squared minus 2x minus 3x plus 6 equals 0 by addition, or kind of reversing, or subtraction, or reversing addition. And this is going to be the same thing as x times x minus 2 minus 3 times x minus 2. And what we did here is we factored, but factored is really just the opposite of by distributing. And then we can distribute again to get x minus 3 times x minus 2, blah, blah. It goes on like this. The point is, this is how we use this arrow in practice, right? Because what this double arrow is saying is we have an implicit kind of under the hood domain here that we get from context, and that is the real numbers. We're using the real numbers everywhere here as a domain, and we can just use this double arrow to avoid writing all those real numbers and just get it nice and simple and say this means this means this means this, and it goes on like that. I hope that makes some sense. I meant to stop like right here, but then I got so into the proof because it's such a nice proof. I love the zero product property. But anyway, I would love to get the zero product property on a bumper sticker. That being that if A times B equals 0, that means A equals 0, B equals 0. One of my favorite properties. Okay. Anyway, any questions on what this means? Good, because it's the most simple thing we're going to do all day. So, now let's do some examples with tying all this stuff together. So, let's say we're going to reuse examples here. Claim. Our claim is that for all x in our set 1, 2, we're going to take all the numbers 1 to 10. X is even implies x squared is even. Actually, let's do the opposite. It's be interesting. X squared is even implies x is even. Yeah. So how can we rewrite that with what we just learned? Well, it's real simple, right? We just don't include the domain. We say that's under the hood. We know what we're talking about, and we'd say x squared is even implies x is even. And then here's where mathematicians get really wishy-washy, not in terms of what they actually mean, but in terms of what they say. This, like what people say when they see this, is they might say logically apply implies. Something like that. Implies, logically implies, follows, all that kind of thing. They basically use all the same language they use for the single arrow, just applied to predicates instead of statements, which is a little bit confusing, but from context it all works itself out. So, yeah. Working on our context clues. Who thought that would come up in a math class? Yes. This is the real, like honestly, like in the pure world of math, this makes total sense. There's no wishy-washiness whatsoever. But because humans do it, we of course bring in our context and our problems, and we make things slightly confusing. That's how it goes. So, however, does anyone remember another way we can rewrite this, getting rid of these conditional arrows entirely? Anyone? Do you remember like what that idea was at least? We don't know the specific one here, but just like the general idea.
Don't you like make the domain like the x is even, and then I don't know, like there's an example that was like for all x in 2, 4, 31, x less than 10 implies x is even, and then you changed it to for all x in 2, 4, x is even. Wait.
So close.
Oh, wait.
Exactly like that. The
Yeah.
idea is, what is this statement really saying? This statement's really saying, remember, this like if we plug in anything that makes the hypothesis false, the statement's going to be vacuously true. So to prove an if then true, all you have to do, I'll write this down. To prove universal conditional show that for all x in the domain, so we're kind of going off this definition here, for all x in the domain that make p of x true, has that q of x true. So because that's what it means, right? For this condition will be true. If p of x is false, then vacuously true, whatever. The only way we can fail here, like the thing we really need to show is that if p of x is true, then q of x must follow. So it's a universal statement, it's a for all statement, right? So we can just use method of exhaustion, right? And just go through all the things that make p of x true and show that q of x must follow. So I'm not erasing it too quick. I'm sorry. I still don't know if I'm gonna write that again. The point is exactly, Lauren's exactly right. So that's what we have to do. But the idea is, when you're proving a universal statement true, you don't even look at all the x in the domain. You just look at all the x in the domain that make p of x true, aka the truth set of p of x, right? So you just look at the truth set of p of x and prove that all those x's must also make q of x true. The point is, though, that's the same thing as just saying for all x in the truth set of D, q of x must be true. In this case, it's the same thing as saying for all x in 1 to 10, such that x squared is even. I think we just look at it, right? So 1 squared is going to be odd. So that's not going to make it even. 2 squared is going to be 4, so that's even. 3 squared is 9, which is odd. 4 squared is 16, which is even. We're looking at all the x's that make x squared even. 5 squared, is that going to be the true set of x squared is even?
Nope.
Nope, exactly. 25 not going to be there. 6 squared, 36. Yep, it's there. 7 squared, 49. Odd, not there. 8 squared, 64. Yep, it's there. 9 squared, 81. Odd, not there. 10 squared, 100, that is even, so it's there. So this is equivalent to just restricting your domain to this, because those are all the places that will satisfy your hypothesis. So for all x in this set, the conclusion will happen. X is even. These two, this statement and this statement are saying the exact same, or all of them. All these are saying the exact same thing because these are all the places you have to check anyway. In order to prove this conditional true, you have to check all the places that make x squared even, and make sure x is also even. Well, these are all the places x squared is even. So you just restrict the domain to begin with. Anyway, no matter how you think about it, let's talk about how you prove it. So proof. And with proof for all statements, I have to use
Truth set?
so we're not gonna, well, there are gonna be truth sets kind of underneath all this stuff, but we're not gonna need that here. Method of exhaustion is what I was gonna get at. It just means check all of them, right? So proof, note that 2 squared equal, so let's say, for example, you started with this claim. We know it's equivalent to this. Let's say we're trying to prove this claim right here. So you could say notes, we'll say 1 squared, 3 squared, 5 squared, 7 squared, and 9 squared are odd by observation, and 2 squared, 4 squared, 6 squared, 8 squared, and 10 squared are even by observation. Observation just means we literally did the math and found which ones are odd and even. Okay? Further, two is even, 4 is even, 6 is even, 8 is even, and 10 is even, also by observation. Now, note that this by observation we'll talk about this later. So really there is a definition for what it means to be even. Being even means you're a multiple of 2, meaning you equal 2 times something. And so later on, later on we're gonna get to a point where if you're trying to prove something's even, you can't just say 2 is even. You have to say 2 is even because 2 equals 2 times 1. 4 is even because 4 equals 2 times 2. But we're not there yet. We're just talking about universal conditional statements. So anyway, if we're here, so we don't worry about, I'll tell you exactly what we have to worry about that. We'll make a code word, and the code word is worry now. That is the exact opposite of what you hear. Like they make T-shirts about like what's that? Keep calm and going on or whatever it is. Like my teacher would be worry now. Now's the time. Anyway, yeah. So we know that all of these are even. The point is, therefore, for any x in 2, 4, 6, 8, or no, in 1, 2, all the way to 10, such that x squared is even, x will be even. Hence, for all x in 1 to 10, x squared even implies x is even. Done. And actually, you know what? Actually, I'm going to say this in a slightly different way. I'll say this. Thus, two squared even implies 2 even. 4 squared even implies 4 even. We're going to keep going like this till we get to 10 squared even implies 10 even. Hence, for all x in 1 to 10, such that x squared, or yeah, for all x in 1 to 10, x squared even implies x even. The point being that we, like, this is the predicate here. X squared is even implies x is even. We check that this predicate is true for all these x's, because the one it's not true, it's factorsly true anyway. So you could write it like this. Yeah, and then you're totally fine. Does that make sense? I mean, this is just straightforward. Like right here, we're just literally proving that we're just showing this predicate is true for all possible inputs. All right, but it's also okay if you're right, kind of like the first thing I wrote, which is if you say instead of doing that whole thing, instead of showing this individually for every single thing in the domain, if instead you got to this point and you said, thus, for every x in 1, 2 to 10, if x squared is even, then x is even. Done. That's fine too. That's totally fine. But I mean, keep in mind that when we're doing this, we're kind of skipping the step of going through and checking each of the x's and showing it is true that 2 squared even doesn't imply 2 is even. 3 squared even doesn't imply 3 is even vacuously. 4 squared even, you're skipping that step, but it's okay. I give you my blessing. Any questions on this? Good. This feels boring. This just feels. We just talked about actual numbers for like a solid 10 minutes, something like that. All right. Let's do one more example, just to give you guys practice. Here we go. This is the dark underbelly of math, and it is logistics. It's a dark underbelly of everything. It's not very idealistic. But anyway, it's just the logistics of how you prove this stuff. So what if we had a claim saying for all, let's say, for all x in SpongeBob characters, I'll say for all x in the space of cartoon characters, x in SpongeBob implies x is an invertebrate. How the hell do you spell invertebrate? Invertebrate? Something like that? You know, I just spelled this the other day in a text. That's what my life's like. Anyway, yes. So for all x in cartoon characters, x in SpongeBob implies x is an invertebrate. And then let's have yeah. So we can rewrite that a couple ways. We could say x in SpongeBob, double arrow implies x is an invertebrate. How else can we write it? What should I have here?
I think you can put cartoon characters.
So the important thing is, right, the original domain is totally cartoon characters, right? And we're saying for any X that's a cartoon character, if X is in SpongeBob, then X is an invertebrate. But I'm trying to get rid of this arrow here again. And so the point is, the idea is I'm going to restrict my domain to say for all X in this more specific thing, X is an invertebrate. So what specific thing am I really talking about here? I'm not really talking about all cartoon characters. What am I really talking about? What's this really making a statement about?
Is it characters in SpongeBob?
Characters in SpongeBob, exactly. For all X in the set of SpongeBob characters, X is an invertebrate. All right. Do you think this is true or false?
It depends on who you include, cause I'm pretty
Any
sure.
SpongeBob character.
False.
So, and who's your counterexample, Safa?
Sandy Cheeks.
Sandy Cheeks, exactly. My gal, yeah. Sandy Cheeks, the squirrel from Texas, totally a vertebrate. Also, any one of the fish, I think, also have backbones. So you got them there. But SpongeBob, Squidward, Patrick, Mr. Krabs, Plankton. You could be fooled for a second thinking, wait, are crabs vertebrates? I have no idea. Anyway, though, we know squirrels are vertebrates. That's all we need. The point is you just need one counterexample. You don't need to prove they're all vertebrates, because that's not what we're saying. We're just saying, this statement is just saying for all, this statement is saying all SpongeBob characters are invertebrates. So disprove, you just need to find one. So disprove. So the way you disprove a if-then statement, right, is to just find a counterexample. And because if you find an example, right, and I'm kind of gonna work with this guy. If we find an example of a cartoon character that's in SpongeBob, but not an invertebrate, meaning aka a vertebrate, right? If we find that example, well, then that means that when you plug that in, it'll make this predicate false. So disprove, let X be Sandy Cheeks. Sandy is a squirrel, so she is a vertebrate. Thus, Sandy is not an invertebrate. However, note, Sandy is a character in SpongeBob. And by the way, you can do like we can have noted Sandy's in SpongeBob first, and then noted she's an invertebrate. It doesn't really matter. We're just kind of collecting facts right now. Right now, we're collecting the evidence, but our conclusion is therefore, X in SpongeBob does not imply X is an invertebrate. Or you'll say Sandy and SpongeBob does not imply. Well, yeah. So the point is we found a counterexample. I'm trying to get too technical with you guys. The point is we found a counterexample. So therefore, it is not true that for all X in cartoon characters, if X is in SpongeBob, then X is an invertebrate. Done. So the point is, to prove a universal conditional true, go through and show that, use the method of exhaustion, show that for all X that makes the hypothesis true, the first part true, show that then the second part's also true. And then you just say, therefore, by method of exhaustion, therefore by method of exhaustion, for all X and D, P of X applies to Q of X. To disprove it, just find one example that shows the hypothesis is true, but the conclusion is not true. Therefore, you found an example where this fails. You just say, therefore, it's not true that for all these characters it works. Okay, any questions on that? Thank the Lord. Moving on. What time is it? Okay. Now let's talk about the new stuff, but we already set it up really well. And that is I'll call it, for all there exists the yin-yang story. So let's talk about this relation between for all and there exists. We've already talked about how the negation of for all X and D, you get P of X. The negation of for all statements are what? If we're saying for all X and D, P of X must be true, the negation of that statement is what? The opposite of that is saying there exists an X and D such that what's true?
Is it not P of X?
Not P of X, exactly, right? The opposite of saying for all X and D, P of X happens is that there exists X and D where P of X doesn't happen, right? You just have to find one. And we just did that with the Sandy Cheeks example, right? We found a counterexample. And then similarly, the negation of there exists an X and D such that P of X. So the opposite of saying there exists an X and D such that P of X works is that for all X and D, P of X cannot work, right? We circled this as a key idea like 3 lectures ago or something. The point is, and we talked about why this is true. Okay, and I'll just do a quick example with you. The negation of for all X in 1 to 10, X squared even implies X even. The negation of that is what? There exists an X in, actually wait. We'll do a simpler example first. Keep that in mind there, we're going back to that. What if I say for all X in the real numbers, X cubed is even. What's the negation that's going to be? So if we're saying for all X in the real numbers, X cubed is even, the opposite of that is that there exists an X in the real numbers, such that what?
Where X cubed is not even?
Yeah, X cubed is not even, otherwise known as being odd. Totally right. And then we can do another one. We can say, how did I write this down? The opposite of so I'll say negate the following. S is going to be our statement, and we're going to say S is defined as the statement some even number, or say some odd number has an even square. All right. If everyone's on homework, how would you go about negating this statement?
Uh,
Noon, office hours closed.
I guess
Can I email
you
them?
can
No,
start with the
no.
domain.
What?
You can start with the, so instead of sum, I guess you could say for all, right? If you're negating it.
Uh-huh.
So for all odd numbers, there is not an odd square. Oh, I'm not really sure.
Yeah, this really is a little bit confusing. This is why I recommend always write your statements in math first. So what this is really saying, this statement, you totally write sums that there exists, right? It's saying there exists an x in the odd numbers. So we're saying there is some odd number that has an even square, meaning its square is even. So there's just an x and odd number such that x squared is even. Oh, boom. Once you have it like that, the negation of s is the negation of this, which is going to be what? You already said, you said for all x in the odd numbers. Actually, Sal, I think you said this exact thing. Yeah, totally. The point is, though, once you write it in math, it's a lot less guesswork, you know? It becomes way clearer. Any questions on this? Real simple. Opposite for all is there exists, opposite there exists for all. The point is we don't need like new quantifiers and new symbols to talk about this kind of stuff. We just realize it's just really the same thing. Now, here is actually, yeah, let's do one example of this. So let's negate a universal quantifier now. So how to negate our universal conditional statement of it? So if we have our statement is, who's got a good universal conditional? I'm tired of coming up with them. Actually, I'm not. I love it. But let's try to personalize this. Who's got one for me? So universal conditional, right? It's the for all x. It's saying it's like for all x and something, x does this implies x does this. What do you guys want? You're gonna force my hand. I'm doing it. For all students, if they're asked to make a universal conditional statement, then they pretend they're gone until I go away. They stay silent. I didn't want to have to do that. Do I have to call you out? No, I'm not going to do that. That one's just too long to write down. What if we say like for all?
I got you.
What's up?
All right, I'm not gonna stay silent on this one. For all LeBron haters,
Uh-huh.
they are a Jordan stan. I don't know if that works, but
They
I
are
know the first part does.
Jordan what?
Stan.
Stan. Oh, fan. Oh, yeah. So this right now, we've written it. This is just a universal. They say they're a Jordan fan. This is just a universal statement. There's no conditional yet. But remember how we can make universal statements from universal conditional statements? We just kind of restricted the domain and got rid of the arrow. We can also do the opposite. We can make the domain bigger and include an arrow. So I like this. It doesn't matter if it's true or not. For all X in people, X loves or hates LeBron implies X loves Jordan. I like it. So that's a statement. So how do we negate this statement is the question. Doesn't matter if it's true or not. Safa, you think it's true?
Yeah.
Maybe unless you live in Cleveland. Maybe we should put for all X and people except Cleveland. Although they've kind of come around to LeBron, right? I mean, he came back, got him a championship. That's enough. The point is, yes. So for all people that hate LeBron, X love Jordan, it doesn't really matter what it means for all people that don't know basketball at all. The only thing is, the point is, how would you negate it? What's the opposite of saying this? Well, first of all, this is already basically in math. So you just do that, make it in math. So then the opposite of that is saying what?
There are some people.
Yep, there's some person, or there exists a person, right? So
Yeah.
there exists an X in person, but you're totally right. That means there's some guy, some person, such that. Ooh. Now is where we run into a little bit of a wall. Because before we just kind of said not P. But how do you negate a conditional again? What's the negation of P implies Q? Now this one, I think we went over this a long time ago. That was like a week and a half ago. But it's a long time in this class, though. I mean, this class moves quick. I think how far I've come. The point is, I think you guys might remember what this is not. This is not the converse. This is not the inverse. This is not the contrapositive. But do you remember?
Is it P and not Q?
Say it again.
Is it P and not Q?
Yes. Nailed it. It's P and not Q, right? Because the opposite of saying if P happens, Q happens is saying that P happens and Q doesn't happen. That's the opposite, right? That's the only row in the truth table that's false. So the only row in the truth table is false is the one where you have P, but Q does not follow. Because otherwise you're vacuously true or P and Q are true, in which case that's fine. So yeah, totally right. This is the opposite of this. So applying it to here, so what we really want to do is the negation of X hates LeBron implies X loves Jordan. But what that really is there is an X in people such that, how would you write this? So it's the P and not Q thing, such that X hates LeBron and does not love Jordan. Regardless if it's true or false, this is how you do it. Does that make sense? And this should make sense in our heads too, right? Like we just got to do this in math, just following the rules, or not really rules, following following the results that we proved with truth tables and stuff. We just kind of followed the math that we got to here, right? But this should make sense. The opposite of saying for all people that hate LeBron, they love Jordan, is there exists some person that hates LeBron and doesn't love Jordan. Right? Makes total sense. So that should line up with our intuition. Anyway, in general, we have is this. The negation of for all x and d, p of x implies q of x. This, remember, is just a universal statement. This is just a universal statement. So we can first of all apply this, where this is the predicate. And so when this is the predicate, we get, okay, that means there exists an x in the domain such that not the predicate, not p of x implies q of x, right? We're just plugging this in for that, right? But then this is equivalent to there exists an x in d such that p of x and not q of x. That's a general form. So this is exactly why when we disprove a for all statement, where we disprove that universal conditional, like the SpongeBob example, we found an example, a counter example, right? Because that's how you prove something exists. You just find an example. Any questions? Okay, good. Now for the actual interesting part in the last 2 minutes here. That's not necessarily incredibly important. No, actually, no, this is the important part. Screw that. This is the important part. Well, okay, the rest is very important to know to pass this class. This is the part I care about. Okay, and that is this. Why? Why is the opposite of for all statement of there exists statement? How can we prove it? Well, so why does the opposite of for all x and d, p of x, why is that equivalent to there exists an x and d such that p of x? So for finite domains, it's easy. Say that d is finite. So it's going to equal sum d1 through dn. For all x and d, could you think of a different way to write that using symbols we know? Oh, for all x and d, p of x. How about make it real simple? What if d was d1, just had two elements, d1 and d2? What's it mean for all x and d, p of x to be true? Let's start simpler. Let's say we just had d1. D was just this set with one element, d1. For all x and d, p of x, what's that equivalent to saying? Right? If there's only one thing in your domain, right? Saying that for everything in your domain, p of x is true, that's just saying that one thing is true. Right? That makes sense, I think, right? So, what if you have two things in your domain? What's this saying now? Well, what's one thing that has to be true?
Isn't it just saying like P D1 and P D2?
Yeah, exactly. A for all statement with two elements is just saying the first one's got to be true, the second one's got to be true. Remember, this is a predicate. So if you plug in any any value, you're going to get a statement. So this is a statement, right? So if we go the full way, thank you, Lauren. If we go the full way and say there's like D in elements here, right? That's just saying that this giant and statement here is true. It doesn't matter how many there are. Saying that for all x and d, p of x is true is just saying p of the first element is true, and p of the second element is true, and p of the third, and all that. For all is basically an and statement. It's a giant and statement. It's saying all these are true. Does that make sense? Now, there exists x and d such that p of x. What's that saying now?
That's saying or.
Yes. Yes, 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 exactly. For all corresponds to and there this corresponds to or. Just one of them's got to be true. This one, or this one, or this one, or this one. Just one of them. And here they all have to be true. This one, and this one, and this one, and this one, this one. Right? Yes. For all is and, there exists as ors. So, let's think about this. The negation of for all x and d, p of x, that's equivalent to saying the negation of for all, the negation of p of d1 and all the way out to p of dn. There's a bunch of those and statements strung together. But how do you negate ands? That one guy with a weird name had a good law about it.
De Morgan's.
Morgan law, exactly, right? Use De Morgan's law, and this is not a formal proof, right? Because De Morgan's law always used with two things, but you can prove it works for more. If you do this for and, you get p of d1 or the negation of p of d2, or, all the way out to or the negation of p of dn. But what's this? What's a bunch of ors strung together? What kind of statement is that?
For some.
For some. It's a there exists a for some. This is saying there exists an x and d such that not p of x. And we get the same thing if we do that there exists. The De Morgan's law turns the ors into an and then it becomes a for all. So this is why. I mean, this should make sense, right? So for finite domains, the for all and there exists are really just compact ways to write all these ands and ors. That's all it is. They're not really special new things. However, how would you prove this if you had an infinite domain? It's a damn good question, right? Like, because for all there exists, they have kind of wishy-washy definitions. Like as humans in English, we know what for all there exists means, right? But as humans in English, we also knew what and or meant, right? But we still decided we needed to define it with a truth table so there's no ambiguity, right? But where's our truth table for all there exists? Like, where is our actual definition of what this stuff means? Well, here it is. For finite domains, that's what it means. This is the definition. So the for all is defined in terms of and, which is defined by a truth table. Good. The there exists defined in terms of the or, defined by a truth table. Good. But for finite, for infinite domains, it's a different story. And the reason you guys have an answer is good because it's a trick question. The answer is we can't. We cannot prove it to be true with an infinite domain just by using like and or proving truth tables, which is why I think I told you in the first day of class, there's like 7 assumptions. There's 7 assumptions, the bedrock of all math. 7 things that we assume to be true and everything else is built from that. This is one of those assumptions. One of those assumptions is that for all and there exists work in this way. That the negation of for all is there exists, negation of there exists for all. That is one of the assumptions because for infinite domains, you can't quite prove it. The point is, though, all this stuff is shored up. So that is class. Any questions on all this? Good. So for alls or ands, there exists or ors, basically. And that is where the yin-yang relationship comes in. Cool. Well, class over. Good job, everybody. Thanks for coming. I'll stop recording.